It is now 1 p.m. Eastern, and in the interest of time, we will get things started. Hello, and welcome to the first May edition of the Insights and Innovations webinar series hosted by the International District Energy Association. My name is Scott Seitcher, and I serve as the Director of Business Development for the association. Today's webinar is titled Decarbonization, Steam is the Alternative, presented by our friends at Maxi-Therm. Before we kick off the presentation, I'd like to go over a few housekeeping notes. This webinar is scheduled for 1 hour, including the presentation and approximately 15 minutes for Q&A, but we can and will run as late as 2:15 Eastern Time if we receive enough questions. This webinar will be recorded and streamed on the IDEA website within about 24 hours of its conclusion. Attendees will also be sent a follow-up email with links to the recording and presentation slides. A link to the presentation slides is also provided in the chat box if you'd like to print those out and follow along. Please submit your questions via the Q&A box during the presentation portion of the webinar. The Q&A icon can be found in the menu bar at the bottom of your screen. Questions will be reviewed by IDEA and posed to the presenters by the host at the conclusion of the presentation. Finally, if you're having audio or video issues, please send a note in the chat function to our host, Jason Beal. Today's webinar is very timely. Many district energy systems run on steam, and there's a troubling misconception among people that steam is somehow outdated. In fact, numerous opportunities exist for steam to decarbonize their operations without sacrificing the versatility and reliability that steam is known for. Today's webinar will cover several important topics, including opportunities for waste steam recovery in power generation and cogeneration, how system operators can achieve up to 95% efficient steam generation with natural gas, and the opportunity to use steam to meet district cooling demands, and more. To discuss these topics and to provide an overview of the benefits of steam within district energy settings, we're pleased to be joined by three highly experienced district energy professionals. Patrick Lach is the Vice President of Business Development at Maxi-Therm. He started in the steam business at age 14 and has spent much of his career documenting and explaining the benefits of steam generation within central utility plants and other applications. Mr. Lach is a graduate of the University of Quebec at Three Rivers. We're also joined by Suzanne Sun Wen, Vice President of ESD, which is now owned by Stantec. She has more than 20 years experience in the HVAC field, including several ASHRAE award-winning projects. Ms. Sun Wen has designed multiple mixed-use high-rise projects both domestically and internationally, as well as central heating and cooling plants. She holds a Master of Science degree in Mechanical and Aerospace Engineering from the Illinois Institute of Technology and a Bachelor of Science degree in Thermal Engineering from Tongji University in Shanghai, China. Last but not least, we welcome Tony Rinaldo, Principal and Chief Operating Officer of Boiler Source. He's been in the industry as a manufacturer's rep since 1979 and with Boiler Source since 1984. He is a past president of the Illinois chapter of ASHRAE and has presented at numerous association and industry conferences over the years. Mr. Rinaldo is a trade ally and presenter for Nicor, Peoples Gas, and North Shore Gas, and is a co-author of the patent High Efficiency Closed Loop Steam Systems. We've got a lot of information to cover today, so we'll get things started. Take it away, Tony.
Thanks, Scott. Welcome, everybody. And let's jump right into it. We're going to start off by looking at this current state of steam technology today. This is a pretty typical illustration of what a steam system would look like. As you can see over here, we've got our typical deaerator, boiler, we've got PRV stations, 1/3, 2/3 valves with relief valves and two drops here, maybe a first stage and a second stage pressure drop. We've got a conventional heat exchanger over here. This would be a steam to water heat exchanger with 1/3, 2/3 control valves. And then we've got our typical steam trap to a condensate receiver, which is vented. That can either be an electric or a steam motive type condensate receiver, maybe going then to a master receiver, which eventually pushes everything back to the deaerator. And then the whole cycle starts again, feeding water to the steam boiler. So that's pretty much, in a nutshell, what we do today. let me show you what we feel is the way to really look at this. We call this steam reinvented. So when you look at this system, the left-hand side over here looks pretty much the same as we saw in the previous slide. But now we've eliminated a lot of infrastructure here because we can take high pressure steam directly into our vertical flooded heat exchanger. We do not control on the steam side. We control on the condensate side. That's this condensate control valve right here. By doing this, we now have high pressure steam coming in. We have that ability now to push condensate without using a pump all the way back to the deaerator or boiler feed system. This allows us to have zero air infiltration in our system and eliminate all of those flash losses that you can associate with a traditional system. Over here on the right is a little illustration of just three different loads. At the top, we've got our zero load, which means that we don't need any heat in our water system over here, and we've got a fully flooded heat exchanger. As we get a call for heat, and we need more heating out on the hydronic end of things, we will start to unflood the heat exchanger by opening our condensate control valve. This allows us to expose part of the heat exchanger. Maxi-Therm received an innovation award for this from ASHRAE back in 2005, I believe, for basically making a variable area heat exchanger. Interesting concept. When we have to go full load, we will unflood the heat exchanger, but we always oversize our heat exchangers about 20% so that we always subcool condensate. We never deliver condensate out of our systems above 200 degrees Fahrenheit. We want to make sure that we don't flash. So, is steam more efficient than most people think? We believe so. Try to imagine a central steam plant that could operate at 95% overall efficiency using traditional equipment that existing staff understands. That dream is a reality by returning cool condensate to the boiler plant below the steam boiler flue gas dew point. Now, we're going to get into more detail of that in a few slides, so just hang on for that thought for a minute. So let's take a look at what makes a vertical flooded heat exchanger a good choice for district type systems. If we look at a conventional heat exchanger versus the equivalent flooded heat exchanger and say that this first example, we're looking at a 4 million BTU process load. If you look at your steam charts, we're looking at about a 959 BTU per pound of latent heat. So we need about 4,171 pounds of steam to satisfy that load. If we do that with a flooded heat exchanger with 100-pound steam, now again, we don't have to have the PRV stations on the inlet side. We can take that pressure directly into our system. And if we design it for a 200-degree maximum condensate outlet temperature, we only need 881 pounds of latent heat because we are going to BTUs per pound of latent heat, because we're also going to pick up 138 BTU per pounds of sensible heat, which gives us a total heat of 1,019. Do the math, comes up with 3,925 pounds, which is a 6.26% savings in steam. If we look at this as a flooded heat exchanger, where we may want to drop the condensate outlet temperature to 130 degrees, which we can do if our liquid temperature, as you see down here, may be in those realm of low temperature like we would use with, say, condensing boilers, right? We can now increase our amount of sensible heat recovered, and all of a sudden, we can use now 9.53% less steam. But let's go take a look at another scenario where we can add a condensing stack economizer. Once we have low temperature condensate coming back to the deaerator or to the steam boiler, we can now condense the flue gas, and we can look at 95% overall efficiency of your steam plant. We'll get to that in more detail in a second here. Let's look at a couple other scenarios. Again, we looked at the conventional at 100 PSI steam, conventional heat exchanger versus a flooded at 100 PSI at 6.26% savings. If we look at condensate outlet at 70 degrees, let's say that we have a very low temperature say, oh, maybe we're heating domestic hot water. Well, we can get a very close approach to that, and our condensate temperature can be much cooler. At this point, if you do the math, you'll come up with about an 18.75% savings in steam. Now, if you look at, say we only have 12 PSI steam, maybe it's a low pressure system, or we have to be after the PRV stations that are in there maybe for other equipment, we can still give you about a 12.18% savings. So there are a lot of advantages to using this type of a heat exchanger. In fact, this one's very interesting because we can take 175 PSI steam, and if we are, again, looking at a very low temperature building loop hydronic temperature, we're in that 90 to 120 range. We can now reduce our condensate to 130, and you still can recover about 10% in savings. So this is all important. So when we get to some slides down the road here, we will have to keep these in mind. One of the things I'd like to point out is this particular case study. This is 2 Liberty, and it's in 2 Liberty Place in Philadelphia. This is a building that was electric, and they were looking at how to save energy. So they decided to go to natural gas. The district loop operator at the time, which was Veolia, now Vicinity, runs that loop. And they convinced them that they should not go with natural gas, but to go with steam. So in this particular case, these are all the things that they did not have to do and were very, very desirable operation. They didn't have to have a quencher. We'll talk about the low temperature condensate that they have to emit to drain. There's no fresh water makeup, obviously, when we do that. There's no pressure reducing valve stations. We're using the high pressure steam directly. They did not need a condensate pump return because we're just wasting, in this case, we're wasting the condensate to drain. No steam vents to the roof, no safety relief valve is required because we will make sure that if say the boilers at that providing the steam were valved at safety valves at 300 PSI, we would just stamp our skid for 300 PSI. The other thing about this being a vertical pattern design is it has a very, very small footprint, and you can get a lot of horsepower, a lot of pounds per hour throughput in a very small form factor. The unit is quiet and with smooth operation. You will not hear a sound from this. There is no water hammer. There's no sizzling or any of that from steam coming through steam traps or anything like that. Very, very quiet. And because there's only one moving part, which is our condensate control valve, very low maintenance. And so you saw in our previous slides, we can reduce steam usage by up to about 20%. Let's take a look at the screen. And this is actually a screenshot from the unit in operation. What you'll see here at 2 Liberty is we're bringing in 129 pound steam, uncontrolled. We have a liquid outlet temperature of 120, which is at set point. So we're maintaining that. We have a return water temperature from the building at 107 degrees F. And our condensate is going out at 110. That's a 3-degree approach temperature. So we have a lot of things going on here. We have a lot of things going on here. And you can see in this particular case, we're running at about 43% of the input load here. And things are just cooking right along. This we also include in our skids a little BTU meter so we can see the actual throughput. Right now we're running at about 5.5 million BTUs. Through this particular skid at about 877 GPM. So this is a very nice thing. No quencher required. Condensate goes right to drain. We save a lot of energy there. Now let's talk a little bit about how do we do this. Well, let's start out with what the DOE says are really good things that we should do to save energy. These are, you can look these up right on their website. These are their steam tips and energy tips. Every one of these is we're going to be talking about here in another slide or two. So what we're going to say today is that there's nothing new, right? We're going to use all standard equipment, standard processes, but we're putting them together with a different recipe. So we like to kid around. We say my carrot cake's a little better than your carrot cake. So I hope you like it. Well, this is what we talked about when we talk about our patent. This is a high efficiency closed loop steam system. What we're doing here, and the key to this, is our low temperature condensate that we can get from a Maxi-Therm vertical flooded heat exchanger. Once we have that cool condensate, we can start doing things with that. We can preheat some combustion air, which is one of the tips that we just saw on the previous page. We can use that to preheat some makeup water or some other process, maybe snow melt, things like that. Once we have very low condensate temperature, we can take that now into the condensing section of a two-stage economizer and bring this boiler efficiency up to about 95%. So this is a calculation based on about a 600 horsepower boiler, 20,700 pounds per hour. This can be a single boiler. This could be multiple boilers. All of this can be applied based on your particular situation. The big thing here is, and the thing that makes this all possible, and here's the actual patent drawing, but this is all possible because of low temperature condensate. Now you see that little gray line right here, right? We're delineating powerhouse versus remote buildings on a campus or maybe in a complex. Could just be a remote room in the same building if the powerhouse happens to be somewhere in the same building. The whole concept here is that we only have steam going out and we have condensate coming back. Everything we need to do to have high efficiency, though, is by the boiler. We don't have access to the hydronic system for these particular heat exchangers. These could be heat exchangers for building heat, for domestic hot water, or some other process. Manufacturing could even use them for processes. As long as we can get this low temperature condensate back, we can do something with it. Once we do that and we reject to our preheat our combustion air, we reject some of that heat to other heat sinks like makeup water or domestic hot water preheat, and we can get our condensate back to our condensing portion of our economizer low enough, we can condense the condensate back before it goes back to the aerator. Now, there are other things that we encourage. Nothing new here. Put a vent condenser on your deaerator. But because we're bringing back all this condensate, we've eliminated the flash losses, and we are really reducing the amount of makeup on the system. You can consider not having to have a deaerator at this point. You can go possibly with a boiler feed if all of your systems out in the buildings are vertical flooded heat exchanger because we have no air infiltration. So something to consider there. This is a case study. This is one of our earlier ones where we were able to proof of concept here. This is actually a customer that was looking for to purchase a new boiler, and they decided to look at heat recovery instead. That's like a two-stage condensing economizer up there on top of a boiler, and they were able to reduce their fuel usage by 152,000 therms a year. They got a rebate from the gas company Nicor for about $136,000. And they reduced annual fuel savings dollar-wise back in the day at about $83,000. So it was a nice case study, and they actually duplicated. They did lather, rinse, repeat 3 times or more on this particular facility. This is another facility that's actually in the background here. That's a 500 horsepower boiler and a 2-stage condensing economizer, which you can see here illustrated in this drawing. Again, great savings. We were preheating some the water going into some process heat exchangers, and they were able to run this boiler at over 95% efficiency. So it's a great concept. To learn more about these concepts and others, please visit our website at maxi-therm-net. Maxi-therm.net, excuse me, videos, or click this QR code or scan this QR code, and we talk about the 95% boiler efficiency system, the hydronic hot water heating system, primary loop, and we also talk about the vertical flooded heat exchanger in more detail. Next up, I'd like to introduce Suzanne Sanyen. She's Technical Authority Mechanical for Environmental Systems Design, now Stantec. And Suzanne, take it away.
Thank you, Tony. Hello, my name is Suzanne Sanyen, Technical Authority from ESD, now Stantec. Next slide, please. The choice between the central utility plant, CUP, And the decentralized system depends on factors like energy demand, geographical conditions, and the desired level of control and resilience. When the facility reaches a certain capacity, the benefit of CUP appear apparent, such as energy efficiency improvement, load shifting within campus, and built-in thermal mass via a distribution network. This benefit could lead to a reduced initial cost, resilient system operation, and a condensed cost of maintenance and manpower. Next slide, please. I would like to use this project to show the CUP sizing and the load shifting strategies. Las Vegas Convention Center West expansion was on a fast track design process. Started in December 2017, the construction was finished in 2021. In June 2021, the West Hall hosted the first show. Las Vegas Convention Center West expansion won the society level 2023 Honorable Mention ASHRAE Technology Award competition under the category of public assembly. The simulated coincident load is used to size the central plant. There are 4 1750-ton 4160 voltage centrifugal chillers with variable frequency drive and 4 4-million gas-fired condensing boilers for cross-flow cooling towers are mounted on the roof of the exhibition hall. The central plant allows us to feel confident without oversizing or adding a redundant chiller, cooling tower, and boiler. As we closely visit the load of each occupancy, the peak coincident load was the basis for finalizing the capacity of the CUP. Next slide, please. There are typically 2 major chill water distribution systems, primary only and conventional primary-secondary system, which means constant primary and variable secondary. Over the past 20 years, numerous ASHRAE, many chiller manufacturers, and other industry publications have provided extensive design guides and case studies on both types. In commercial buildings, variable primary and variable secondary can be the third choice in a 5,000-ton or higher CUP with a high fluctuation in load profile. This system will make the operation and the maintenance easy. It is also enhances the resilience of the system by avoiding the key pressure-independent bypass control valve in the variable primary system. I have done articles and seminars discussing the distribution system and central plant operation and control. Please reach out for further info exchange if you'd like to. Similarly, to offer the most flexible combination of operation pattern, chillers, cooling towers, primary distribution chill water pumps, and condenser pumps are recommended to be arranged into one-to-one interchangeable standardized form. Next slide, please. We all agreed that central plant is the powerhouse, the epicenter, and the building plays a critical role in consuming energy and emitting greenhouse gases. Currently, for most states and the legislation, buildings are governed by the IECC code. The map shown here covers the adoption status of the IECC in each state across the US. Energy Code, IECC, or ASHRAE 90.1 set the energy-related requirements for building elements and system. Next slide, please. In January 2021, the Biden-Harris administration launched the coalition of state and local governments to strengthen building performance standards, to advance legislation or regulation in each of the represented jurisdiction by Earth Day 2024. Here's a map indicating the coalition members of BPS in the US. Next slide, please. There has been ambitious US goal of achieving a carbon pollution-free power sector by 2035 and a net zero emission economy by no later than 2050. Both energy code and building performance standards address the same goal, decarbonization of the built environment. Some proposed systems cover some of the solutions for certain type of the building types. But the situation is flawed. For instance, water source heat pump or VRF with thermal storage might not fit hospital occupancy. One of my projects in Chicago actually faced the fuel source challenge. The electrical demand of a fully electrified building in Chicago is determined by winter load, not cooling. After early cost estimation, a solo source of electricity become too expensive to build. So cost plays a critical role in commercial buildings. In 2020, commercial buildings consumed 18% of the energy in the US. 35% of the overall consumption is electricity. The state of California is a leading state implementing energy standards. However, HSCI also published a code update, which requires both heating and cooling system in nursing homes backed up by an alternative source of power with 96 hours of operation. Next slide, please. District energy plans serve multiple buildings or whole district. Centralized CUP, it generically contributes to the overall decarbonization and a more sustainable approach to energy production and consumption from many aspects, such as energy resilience, optimized resource utilization, integration of renewable energy sources, and energy storage. This project is a design-build high-rise office building in Denver, Colorado. Our office worked with Xcel Energy, the district chill water company, to implement a warmer chill water return discount, supporting a water source VRF system in this 30-storage office building. Next slide. Let us do a quick fundamental overview of the chillers. There are mainly two types of the chillers: vapor compression refrigerant cycle and vapor absorption refrigerant cycle. On your right is a centrifugal chiller. A single effect absorption chiller is on your left. Which model uses the lithium bromide and water solution? It's used the hot water as a heating source. Next slide, please. Both absorption chillers shown on this slide use lithium bromide water solution. Double effect on your left, you can see it uses steam as the driving source. The single effect type is the one on your right, use hot water with the flanged connection. Next slide, please. It is important to note that COP between centrifugal and absorption chillers are calculated differently. AHRI indicated working conditions to measure COP. Centrifugal chillers are measured with a cooling effect over the compressor work input. For absorption chillers, COP is then calculated by the cooling output over the heating source input. The COP for absorption chiller is low under this measuring metric. Regardless of the solution of the lithium bromide ammonia refrigerant is water. Absorption chillers have low greenhouse emission Without a compressor, instead of using only a solution pump and a refrigerant pump, the operation is very low. Also has minimum impact on the electric grid. It has fewer moving parts, however, with more components, absorber, evaporator, generator, and condenser. The footprint is a little larger than the centrifugal chillers, as well as links to the initial cost. The cooling tower capacity requires a little bit more capacity compared with the same cooling output centrifugal chiller. Next slide, please. This slide provides a sample comparison among 1,000-ton output centrifugal chillers, single effect, and double effect chillers credited to York. The data on the top table shows that although the absorption chillers have low COP, however, you could tell the electric consumption is extremely low. The bottom table lists the operation and output range for both type of absorption chillers. Both of them utilize lithium bromide solution. Next slide, please. Next slide, please. High pressure steam, especially with a pressure higher than 100 psi, steam turbine-driven centrifugal chillers can also be utilized to generate chill water, like Carrier Turbine Chiller 17DA has a capacity range from 3,000 to 5,500 tons. York model YST on your right is powered by the steam turbine and covers a capacity from 700 to 2,800 tons. Next slide, please. Those projects are not mine. Case studies can be obtained by York. Actually, York installed the turbine chillers for those projects. They've been utilized majorly for cooling backup, load shifting, along with CHP or other alternative fuel source. Next slide, please. As someone from Chicago who is interested in reducing carbon emissions, I can't help but envy other cities that have the option of using district steam. District steam or waste heat can be the source of not only providing heating and domestic hot water, but also offering cooling options to the buildings or campus through the use of absorption or steam turbine chillers. These solutions have been in operation for over several decades and are reliable alternative to electricity-based cooling. By using district steam, we can reduce our reliance on the electric grid and make a green step towards more sustainable energy resources. That is all from me today. Please reach out if you would like to discuss system optimizations in the future. And now, please allow me to introduce Patrick Luck, co-owner and vice president from Maxi-Therm. Thank you.
Thank you, Susan. You did great. It's rare we found people that know steam cooling, so thank you for your time. All right, so let's move on, Tony. Let's show the next slide. First thing first, guys, as you all know, electric demand is going to the roof. Cloud servers, electric cars, I think it's a great thing. Automation, robots, digital currencies. So these numbers have been taken from the American organization there, Energy Information Administration. So just showing you electric demand is going to the roof, and we want to do this. Tony showed a picture. We want to put these everywhere, right? Just increasing electric demand all over the place, which for us, it's a nonsense. So let's move on. So right now I am downtown Detroit. We have two nice units using central steam, a book tower, very nice building, and the one in construction, Hudson building. Actually, I'm right behind that building, but unfortunately the sun is too high today, so I cannot show you the building live, but this is what we do. We are a big fan of using steam district energy. Next slide. So for one thing that, to come back to Suzanne, is this chart shows that most of the building, 20% of the electric needs, it's for cooling. So why not, if it's possible, remove that electric demand on the electric grid from heating and cooling? And because I didn't mention yet, it's probably on the next slide, but steam has the same dream than electric. Right now, we're putting all our eggs in the same basket, right? I never saw a book saying putting all your eggs in the same basket is a great thing. And that's exactly what we're doing. And with steam, it has the same dream than electric. And what's the dream is that one day all the electric will be generated by green source fuel, while steam can be generated by green source fuel. Today's world, natural gas is the greenest fossil fuel, but tomorrow we don't know. Biomass steam boiler exists, biogas steam boiler exists, hydrogen can be done. There's all kind of green source fuel that we can use today. Let's move on, Tony. So yeah, that's putting all our eggs in the same basket. And not that I'm against electric. Like I said, I think electric cars is a good thing, but it's not reliable right now. The electric grid is not reliable. Those numbers are facts. When Hurricane Sandy hit New York, they all lose power, but not steam, and buildings can have steam still heat, you know. So that's the number of power outage that happened in those 5 states, which is 30% of the population. So yeah, let's move on this also. So that, like I said, we're a big fan of promoting steam district energy. And I think we need to stop also thinking a big steam district energy. It can be micro steam district energy. New Home, Minnesota, a little town in the middle of a cornfield in Minnesota, 15,000 people. They have a steam district energy loop because they believe that one day they won't burn natural gas anymore. And they do cogen also at the same time. So steam for us is resiliency, fuel flexibility. So, I mean, energy security is very important, you know, lower capital costs, energy security, low pumping input. We'll discuss more in a little bit about that. 90% energy conversion possible with natural gas, what Tony explained to you earlier. Hold on, I'm gonna remove this. On-site electrical generation possible, provides heating and cooling, electrical grid relief, big time, potential for carbon capture. So if this technology improves and you want to install that in small boiler room, well, it will cost way more than using it, apply it on a big central steam plant, you know, adaptable to any future fuel source. And I'm a big fan also of the waste to energy. I know there's people that had bad experience in their life. I think the technology has improved a lot. Actually, IDEA in 2025 will be in Minneapolis. There's a great waste to energy power plant down there, doing cogen, and distributing steam across Minneapolis. So that's the best way to get rid of our plastic island on the ocean and landfill also. Anytime you design a new hospital, for example, well, you know that around that hospital, there will be hotels, probably shopping malls or clinics, other clinics, offices, or maybe a school also. So why not do a mini district energy and distribute heating and cooling across those buildings with doing cogeneration at the same time? So there's all kinds of ways to relieve the electric grid from heating and cooling and plan for the future. Because, for example, when Denver is the oldest district energy in the country, 1880, and New York, Seattle, Boston, Baltimore, name it, they were all burning coal. Once they all decide to switch to natural gas, They didn't change anything on their infrastructure, on the steam distribution system. They didn't change nothing. Well, same thing with electric, right? So why is the same dream? Same dream. One day we can burn something that will be green, or have the technology to make it green, and making cooling and heating for a small or big city. It's possible. Next slide. Just some reminders. Those pictures shows that the one here in the middle is a steam turbine, small one, can be small as 50 kW to generate power. Then the one on top right, the gray one, this is turning a fan. So I'm not saying a small fan, but a big fan can be turned by a steam turbine. And then in the middle, it's a pump that you can run a pump with steam also. And of course, the steam absorption chiller that Suzanne just been through. So again, if my steam is green, well, who cares about the efficiency today, right? We want, and also it's really, really reliable. I'll discuss about reliability of steam in a few slides, but keep that in mind. Nobody losing steam, right? So I don't see that happen too much. Next slide. Okay, let's go through a small, quick hydronic versus steam, because a lot of people think the hot water is more efficient. So keep in mind what Tony has presented earlier, 95% efficiency possible with a steam boiler. And by the way, if you install the vertical flooding design everywhere in the city, in the campus, and the building, this become 100% closed loop. So no more de-aerator, gone. Chemical costs down, surface blow down. There's a lot of savings. You don't need a de-aerator anymore, just a feed water tank. You don't have any fresh water, very, very minimum, right? So keep that in mind, the concept of Tony that explained versus hot water for 35 million BTU loop. So that's a job that came out for bid in the federal prison in New York State, I will say 7 years ago. And we took that that spec and we decided to challenge if they would have go primary loop steam instead of a high temp hot water. So next slide. So just the pumping, let's talk about the pumping. So for a hot water loop, you need pump for each borders to get in the loop, and then you need a main pump that will feed the whole building, right? So compared to a steam system that you need one feed water pump to feed the from the DA or the main receiver tank directly to the boiler. Let's move on, Tony. So with 75 Fahrenheit rise, not 40, not 20, with 75 Fahrenheit rise hot water, you will need 937 GPM of water, which means 468,000 pounds per hour of mass flow, mass energy, for a total pumping of 90 horsepower. The same steam system to generate 35 million BTU, you will, in a closed loop system, you will need only 69 GPM, 35,000 pounds per hour of mass flow energy. This is huge. Huge difference in electric grid relief. Also, this is tremendous numbers. Next slide. So just on the pumping aspect, you're saving 200 tons a year of CO2, carbon footprint reduction. Next one. So you want to know more, because actually those numbers are way more. There's way more saving. So go see those videos. You got what Tony explained you more in details, the 95% steam boiler efficiency with 100% steam condensate closed loop, the hydronic versus hot water system I just been through, but more in details with higher numbers, savings with the fuel and everything else. And of course, the vertical flooding design more in details. Next slide. Okay, let's go through some benefits of using steam. Don't go too quick, Tony. So steam is visible, non-flammable, non-toxic, has no electric shock hazard. It's really safe, really, really safe. Steam is safe and reliable. When a steam leak happens, it's never an emergency. How many times I went in a mechanical room, I see a steam leak, I go back 5 years later, it's still there. When it's new, everybody's happy. When it's getting old, like old steam system of 100+ years old, leaking everywhere, and nobody's fixing them, but no building is losing heat. This is how reliable it is, right? If it's a natural gas leak, everybody out of the building, or traffic jam downtown, hot water leak, you better take care of it right now because you're gonna have a hell of a mess. Steam, there's nothing to worry about a steam leak. Actually, watch the next picture. She's my lovely wife, downtown Detroit, where I am right now. I asked her, can you stand on the cone, honey? Is it too hot? She said, no, it's not too hot. So she's standing on the cone, and to make sure that nobody hit the cone, they just put a little orange cone there at the bottom that you can see, and people are driving through that cone, and all the buildings that you see around, they're all on steam, and nobody's missing heat. Nobody. This is how reliable is a steam system, and people have a tendency to forget about that. And I think it's the biggest asset of a steam distribution energy system. Next bullet point. Possibility of having a condensing steam boiler with 95% steam generation efficiency on natural gas. Possibility to have a building with no vents, no chimney using steam district energy. So the vertical flooding design, there's no steam safety relief valve, there's no flash tank, no vent to the roof. And if you bring steam district energy, no chimney whatsoever. One thing I forgot to mention, Vicinity in Boston, they're putting in giant electric steam boiler, which I think it's a great idea. It's a great temporary plaster, you will say, for some of you, because electric is not 100% green yet. But for the buildings, they don't need to, they need smaller substation, electric substation, because all the heat is not coming from the electric grid. Well, if they were providing cooling the same way with steam chillers here and there in the city that will supply cooling water for, I don't know, 10 building here, another 10 building there, well, the electric substation will be much smaller. So that's another thing that's another benefit of the steam district energy system. Steam can be used for heating and cooling using technologies proven for over 100 years. You can generate steam for multiple green source fuel with proven technology and biomass steam water, biogas, solar, hydrogen, nuclear, waste to energy, and unknown future fuel. Next one. Steam turbines can generate electric power and can also run pumps and fans. Steam only needs a small pump for boiler feed, use less than 1/10 the pumping energy of a comparable hot water loop. So go see the video. Carbon capture is easier to consider with a central steam plant, especially including cogeneration with a steam distribution system for heating and cooling. And you know, when you have low condensate temperature, it allows you to use non-metallic PEX piping for a condensate pipe, because we can provide low temp condensate under 200 Fahrenheit at all time, depending on your hot water set point. Next one. I will let you with this final slide. Like I said earlier, I'm a huge fan of waste to energy. This picture of me was taken in the airport of Minneapolis. They have a super waste to energy power plant just beside the baseball stadium of the Twins, and providing steam. I also invite you to go see on YouTube Copenhagen Waste to Energy. Go see that unreal power waste to energy power plant. They did a ski hill with it to make it approved by the population. Technology exists. I think is the best way to get rid of our plastic island and landfill. Yes, thank you very much. Is there another slide, Tony? Oh, Scott, I think you want to get in. Well, we'll be at the IDEA in Florida, in Orlando, booth 43 and 42 and 43. Come visit us. Thank you very much.
Yes, first of all, Patrick, Tony, and Susan, thank you, so much for a terrific and very informative presentation on the benefits of steam, its wide uses, and dispelling some misconceptions that might be out there. What I plan to do, we have received some very good questions, for each of you, from the audience, and I'll try to not just load up, questions to one presenter and then the next. I'll try to bop back and forth between the three of you. Patrick, since you were just speaking, I will actually start with you. We had a question come in. This is a bit of a manpower question. Do you need a station engineer to work on high pressure steam systems in order to make hot water?
No, actually, I mean, I'm not talking about the steam boiler, but if you're using a high pressure steam vertical flooding design heat exchanger, no stationary engineer is required.
Okay, thank you. That's an important distinction, especially considering the labor shortage that's going on in the industry. Susan, we had a question. Let me phrase it this way. The low-cost steam that you discussed during your presentation, what would be the energy rate in order to make that type of cooling done economically?
That's great question, actually. I would say is that regularly, if you depends on the pressure. If you operate your steam plant yourself, the price can be almost like from $8 to $12 per 1,000 pound, for instance. But the study we did over the table, if you could say the savings, if you happen to have waste steam, for instance, as long as the price could be quarter of the regularly operated steam plant, and then they could be breaking the balance. So operating the cooling become more economical by utilizing steam. So waste steam would making more sense, or you could simply using from the district steam, which is normally they would offer lower price for summer usage. Thank you.
Thank you. That was a great answer. Tony, we had an engineering-oriented question. When using a vertical flooded heat exchanger in conjunction with a low temperature hydronic building heating loop or other type of low temperature system, when something like that makes sense, is there still a boiler efficiency advantage if the condensate returns is above 130 Fahrenheit?
That's a great question. And we have plenty of systems like that out there. The key here is to try to maximize all your I should not maximize, but minimize all of your losses. So if you're doing a steam system that remotely in either another building or another room where we have vertical flooded heat exchangers and we're not returning condensate below 130, yeah, you're going to have some savings. Every degree that we can save on our condensate return temperatures has less losses on your condensate return lines. Also, because we're using less steam, you can also size your steam piping to be smaller because we're getting more BTUs for every pound of steam. So there are some advantages of doing that. Are they small? Yes. Are they negligible? No. So I always tell folks that we have to look at the concept and run the numbers and see what makes sense. Obviously, if the one thing that you will get in a huge advantage by using the vertical flooded heat exchangers is that you won't get any flash losses. There is condensate is at a low enough temperature that it will not flash. And depending on what pressure you're running at, those savings can be somewhere between 3.5% and 13%. So just from flash losses, and no flash losses also means that you don't have makeup water. Hope that helps.
It did, and actually we got a question from an attendee. He said, she said, what are flash losses? Can you provide just a quick working definition of flash losses for anyone in the audience who's not familiar with those?
Absolutely. In conventional systems, when we work on conventional systems, work on just taking out the latent heat from the steam. So if you've got, say 5-pound steam at the heat exchanger, you're going to be coming out at about 227 degrees for the condensate. When that condensate goes through the trap and then hits an atmospheric open receiver before it goes back to the boiler, you cannot have liquid at a temperature at atmospheric pressure above 212 degrees. So it flashes. And at 5 psi, that flash loss is right around 3.5%, 3.6%, something like that. So that's what a flash loss is. Then when that condensate goes back and it keeps going through these atmospheric receivers, if it's hot enough, it will always flash. So that's what we're talking about, is just the difference coming from a pressurized system to an atmospheric and the temperature differential to get down to that magic number of 212 degrees. That's why we designed for 200 as a maximum, make sure we have a nice buffer below that 212 number.
Thank you. And our next question is for Susan, and she might actually be typing the answer right now, but I think it's a really good question that,
Sure.
I want the audience to hear. Question came in during your presentation that you suggested that steam systems can allow folks in the audience to reduce their dependence on electric cooling. With that said, what sources of renewable energies are available for steam generation that would work well with the input temperature requirements needed for the use of absorption chillers?
I would like to, this is a great question. I would like to mention one thing for absorption chillers though. Absorption chillers actually is surprisingly work with a very wide range. For instance, they could work with hot water, they could work with pressure, steam with different pressure. Speaking of the hot water, they could work as low as 135 degrees of water, or as high as some even high pressure overheated hot water. And for steam, they could work along with like as low as a low pressure steam lower than 15 psi, or they could go all the way up to 100, even higher pressure steam. So with that being said, is that absorption chiller, it is really having a wider operation range or operating conditions than you thought of. And to answer the question straight is that currently, as far as I know, especially for, if I recall correctly, 2 years ago, we were working with a Honeywell CHP product. I think it's STL. I do not recall exactly the model number. They could have the option of the fuel source. They can do same machine, they can operate, of course, natural gas. They also be able to work on along with the biomass and the hydrogen. Although hydrogen right now is kind of like difficult to obtain. As far as I know, starting from along with the DOE, I think at least in Middle West, I think Tony, you probably know better than I do. There will be a hydrogen distribution line started, would be when would be that time? That I do not know, but it's been already started. They having a delivery date set up already, try to supply from Indiana all the way down to Chicago, providing hydrogen. That's what I understand and what I knew of. Tony, if you could tell me, I would appreciate. Yep.
Yeah, there is hydrogen hubs going into the United States. There's, I think, 7 or 8 of them that are currently in there. There's one about 19 miles from downtown Chicago that's in process. And you know, hydrogen right now, the DOE, the government is giving a $3 per kilogram credit for that. Illinois and Colorado are the only 2 states right now that are also putting a $1 kicker on that. So you can get $4 per kilogram of hydrogen produced. So if you want to do hydrogen locally at your own facility with an electrolyzer, you can do that and you can get that. And it's a guaranteed kickback for 10 years from the government and from the state of Illinois or Colorado. So that's possible. There's ways of cracking hydrogen out of ammonia. We heard about some very interesting technologies at the ABMA conference a couple of weeks ago, and you know, there's also you know, there's a lot of research going on. There are billions of dollars right now being spent by the government and other entities to research more carbon-friendly fuels. So that, you know, let's face it, there are a lot of natural gas pipelines around the United States. And I doubt very much that they're going to be just sitting there empty. and everybody's going to electrify. I think that those pipelines are going to have to carry some other fuel or blending of fuels at some point. And it's a process, right? It's a pathway to get to decarbonization. We're not going to flip a switch overnight. It's going to have to happen over the course of many years, maybe even decades, but we'll get there. But don't discount a fossil fuel system just because the fossil fuel that's in it today, you don't want to burn. I hope that helps.
That's a very good point, and that actually addresses a question that came in from an attendee, and I think his or her dilemma was, if I'm reading this correctly, that for their system, they're under pressure to move away from natural gas, and the question became, what else might be, what else might be possible. Tony, you and Susan have just, you've mentioned hydrogen, you've mentioned biomass. Again, there might be fossil fuel, emissions associated with those. But again, it sounds like one of the things with steam generation is that it's not completely a marriage to natural gas. There are other things, that are in the, coming down the road that are going to supplement natural gas, at least in the, over the next, few years or decades. Patrick, a big picture question for you. Are you, in your capacity as someone C-level at Maxi-Therm, are you seeing more or less demand for steam projects both in the United States and Canada?
That's an interesting question. What the thing that has changed over, I will say, only the last 5 years is we have more and more demand for big units. So, and I know that most of them is to do like mini or micro hot water district energy. So they're going to bring steam for, I don't know how many distance, because it's easy to transport, right? 1 pound of steam travels 10,000 feet per minute, and 1 pound of water is only 600 feet per minute, just 1 pound. So anyways, so they're going to bring this in that area. Hot water will be fed for 5-6 buildings. So to answer your question, there's more and more demand for big units. Like recently we had the biggest order, not in terms of dollar value, but in terms of size of the unit. It's a 65 million BTU unit using 100 psi steam, and that means around 2,000 horsepower for the people that had a better picture in horsepower. So 65 million BTU, it's a big size, big one.
Thank you. By the way, since we are now at just a little after 2 o'clock Eastern, there are a few more questions that I would like to get to. So those of you who can, in the audience that can stay with us, we encourage you to do so. Question that came in during Tony's presentation. So I'll pose this to you, Tony. How do these steam systems accommodate boiler cycling, and purging, specifically when boilers are oversized? Would this still, when those boilers are oversized, would this still be an appropriate application in your opinion?
That is an outstanding question. One of the biggest things that we're seeing today, and this applies across the board for anything, is right sizing equipment. But one of the biggest things that's happened over the last 10 years in the boiler industry is getting burners that have high turndown. So we push and we promote high turndown, low excess air burners. So we make the burner burn as efficient as we can. And, traditionally, if you had, say, a boiler that was 300 horsepower or larger, 10,000 pounds per hour or larger, the burner might have had a turndown of 5-to-1. That means it would run from 20% to 100%. Today, the de facto standard is 10-to-1 turndown. So we've doubled that. So we can run from 10% to 100%. So even with the diversity that you need based on your load changes, today the operation here is to try to have basically cruise control for your boiler, right? We want it to sit there and just hum along at whatever speed it needs to satisfy the load and not cycle. Because you are correct, cycling off is a problem. If you're in a situation where your boilers are large, they're oversized, and you just can't get a burner with enough turndown, you might want to consider a base load boiler. A base load boiler is just a boiler that's a little bit smaller. If you've got a 100,000 pound per hour boiler and its turndown is only down to 20,000 pound per hour, maybe put in a boiler that's say 20,000 pound per hour that can now cycle down to 2,000 pounds per hour. So those are some of the options. Be more than happy to talk about it. Send me an email.
Thank you. I want to get back with another question for Tony. This is a little in the weeds, engineering. Is the vertical heat exchanger utilized in similar fashion as a traditional kettle reboiler, which has controls for the condensate level?
Maybe it's similar. I'm not sure. I mean, it's horizontal. It's different. It's a different process. Yeah, Tony, go ahead.
Yeah, a reboiler is just what it sounds. It is evaporating. We're condensing. Okay, so a reboiler is using a hot water or some heat source in the tubes and causing the water in the shell to heat up and boil, right, to create steam. So it's a little bit different. We actually have a thing called the clean steam generator, which is a reboiler. We're using high pressure steam to make low pressure steam. Right, it's not the traditional hot water to steam type things, but that's basically the difference.
Okay, thank you. That's a good answer. Susan, another question. Do you have an opinion on what type of infrastructure makes steam generated cooling feasible?
Well, based on my experiences, that I want to say is that if you having a district steam available, that would be the most easy way to have that available. For instance, one of the project in Indianapolis, we noticed that Indianapolis, the Citizen is the district steam company name. They offer surprisingly lower price if you want to do utilizing steam during the summer months to generate cooling. That's a specific credit for that. And the rate is surprisingly low. And also we feel like the other thing is that if you're using CHP, you generate your power on site, that waste heat is unavoidable, either heating with hot water or basically probably available is a low pressure waste steam. That would be a terrific source that utilize that to compensating for the cooling generation. So usually those are the two I've been seeing and then being able to recommend. Thank you.
Thank you. And another question for you, Susan. You were kind enough to type in an answer to someone's question that they have a follow-up to that question. I'm going to read the original question, which you answered. The original question was that you had said during your presentation that once the loads reach a certain size, a central utility plant is more feasible. And then they asked you, do you have advice on how that size is estimated, and is there a standard to follow? And your answer was that you would suggest as low as a 300 ton. The follow-up question to that was, how did you come up with that number? And is there a formal procedure to follow for folks who are not as experienced as you, in that area?
Right. So usually in our office, this is a great question, because usually in our area, before we answer the question, you really should do almost like a engineering analysis. You based on your load and based on the power consumption, say if you do not want to prefer to do a central plant, so that probably you would end up with air-cooled option. For the air-cooled option at a certain capacity, the air-cooled option, basically it range around, say, between 1.5 to 2 kW per ton. We usually, of course, some of them is more efficient, some of them is less efficient based on the more ASHRAE 90.1 updated, the system compliance. So we base on that ratio, and then you base on the water-cooled option, which is whenever you reach to the 300 or a higher capacity, your peak kW per ton, usually around 0.6 or lower. Some of the, it depends on what type of chiller you have, mag chillers or a different type of the chillers, for instance, even you use centrifugal. And then the IPLVs is greatly also improved. So if you do a life cycle cost or annual operation cost, along with the peak value and also the cost of tag along with the utility, that's usually how we come along with the power consumption. Of course, you have to analysis the, I want to say, the initial cost along with the operation cost as well. So based on, I have to under one condition is that I would assume the question, the type of the building is applying to the commercial building. So with that being said, is that because if it's for the other, any other like a warehouse, it does not apply. That may not apply. So if you get all those variables together, what we're feeling is that based on the number initial cost and annual cost, operation cost, 300 ton usually starting is like you're starting to see centralized plant making more sense. And also probably around 150 ton, or you can start it with 2 chillers and the system operation or distribution. That's another factor you want to look into that as well, for sure.
Thank you. I'm going to try to sneak in 3 more questions before we wrap things up. I'll start with a quick one to Tony. Tony, when you preheat combustion air, do you need a special burner? Is that required?
No, you don't. I mean, the temperatures we're talking about, we're trying to limit the combustion air to coming into the burner under 140 degrees. We usually target 120, 130, and that picks up a couple of points of efficiency. That way, if you want to go higher than that and you have the ability to go higher than that, you can, but then it usually requires a specialized burner. Most of the UL components are rated about 140 degrees off.
Thank you. A question that maybe perhaps one of you can answer. I'm not sure. It has to do with biomass. Question came in just a few minutes ago about of the various biomass fuel options that are out there for the types of steam generation that we've been talking about. Is there a preference on the biomass fuel type, such as is pyrolysis necessary? Would biochar be better? Didn't know if any of you had any thoughts about that specific to biofuels.
No, I don't. Tony, do you have? I think I'm not a specialist with biomass boiler. I think anything can be great depending what's your available biomass source nearby. That's the thing that need to be considered.
Yeah, exactly. I mean, once you've identified a biomass source and you can look at its carbon footprint and what that will cost, those are all the main considerations. As to the preference, that's pretty much by manufacturer. I mean, somebody will have to determine whether or not their piece of equipment can use that fuel source.
Yeah, and one thing I'd like to add, Scott, is and hopefully on the call there's boiler operators or people involved with a boiler or whatever. I don't think if you can replace everything and go biomass or biogas or hydrogen, okay, great. But if you can do 10% of your steam with biogas or biomass, a small biomass boiler, because whatever you have source fuel available nearby, well, that's a big gain today. So I don't think you can do step by step. And by the way, same thing with the waste to energy, because I want to push that, but you can go as low as 100 tons a day compared to Minneapolis. I think is more than 1,000 tons a day. So you can go quite small, and a big campus, I think you have tons of trash to get rid of. So, and today technology exists to make it compact, flue gas look nice, and yeah, so things can be considered like that, not change everything overnight.
You know, that's a great comment. You know, I mean, I remember as a kid, I was always told, how do you need an elephant? One bite at a time. That's exactly how we have to attack this problem with decarbonization, is one bite at a time. It's a process, it's a pathway. Looking at hybrid systems or systems that can be developed and upgraded as time goes on is very important.
Thanks. And it sounds like what, big picture, what you're saying, Patrick, is that, just as investments should be diversified, fuel sources should be diversified. And to the extent, even if, it produces a, relatively minimal amount of, your power, heating or cooling needs, that there are some benefits there. And you're getting your staff experience at working with either different types of equipment, different types of fuel sources, and so on, to not have all, as you said earlier, all your eggs in one basket.
Yeah, no, exactly.
The final question I'm going to pose before we wrap things up, because I think one woman asked this question, and I think it might be indicative of some other systems out there. If I'm interpreting her question correctly, is that it sounds like her system, she's a district system that in the long term is planning to move to a low temperature, hot water system for carbon reduction, reasons. But in the short to medium term, she is asking, essentially, is it still wise to, use steam such as phasing distribution, building transition projects over the next 10 to 20 years? How feasible is that? And what is the lifespan of this type of heat exchanger? Because it sounds like she's trying to balance her system's long-term plans of a low temperature hot water conversion with perhaps the equipment that they already have or could look into for their immediate needs. So just wanted to pose that question to the panel.
Tony, you want to start?
I
can start.
Go ahead.
Well, first of all, I will say I think it's a mistake to go low temp. Go see the video, hydronic versus steam, please do. And number two, yes, it can be done. And by the way, the longevity of a heat exchanger, I will say it's more than 50 years. How many times I went, even a conventional shell and tube, I mean, I saw plates of 1960 or whatever, 1950, and didn't replace a bundle yet. So it's more than 50 years, in my opinion. We never replaced a bundle so far on our heating system. Not even close. I don't know if I answered the question well, but you can go low temp with steam as well, like I showed you, and it's easy to distribute steam everywhere. No big pumping needs. If your mindset is to relieve the electric grid, because it doesn't make any sense to put everything on electric. It doesn't make any sense to me. So if you can relieve electric grid pumping, also heating and cooling, I think it's the way to go. Definitely, it's the way to go on a long-term vision, of course.
Yeah, if you're considering doing a steam to water conversion like that in the future, we'd love to talk to you about it, because it's something that I think once you hear all the advantages of these types of systems now today, making steam relevant again, I think it's important to look at that, because you don't want to abandon your infrastructure and put in a whole new, very expensive infrastructure system when you can reuse and repurpose the existing steam infrastructure.
And one thing I'd like to add, Scott, is there's two ways to go low temp, right? Let's say you're in a big campus. Number one way is you're going to run natural gas pipe everywhere on the campus. In every mechanical room, you'll have a condensing boiler, I guess, to do low temp. That's number one. Or number two, you have a distribution system of hot water all across the campus, okay? So let's say it's 50 years old. You're going to start to have natural gas leak in scenario one, and that will be emergency care. In scenario two as well, we're going to start to have hot water leak, and it's going to be emergency care. It's much more a headache than repair a steam leak, much more of a headache. So if you think long-term vision with the maintenance guys gone and everything else, you can simplify everything. I mean, no more PRVs, no more condensate pump. These are all pain points in the maintenance schedule of any steam distribution system. So we make it very, very easy.
Can I chime in
Yeah,
real
go ahead,
quick
Susan. We
on
never
top
let
of
you
that?
talk. Go ahead.
No. I just want to chime in one thing. So converting from steam with future, maybe a low temp heating hot water. One thing I would like to remind is that because currently a couple of the project in our office were facing that. Couple things. Some of the building on the campus, we utilize the steam currently, and there's in consideration switch away from the steam into the condensing boilers actually. And so the campus, some of the building on the campus, they're utilizing the heating hot water generated from steam, which is 180, 160. And because of in the future, they are going to utilizing the condensing boiler, and some of them is even lower temperature. That ends up that the air handling unit in those several buildings have to be derated because we're having different temperature to serving those, the heating coils. So that's another thing. Maybe down the road, potentially there are several issues correlated with this conversion. If you want to have that conversion, we have to, there are unavoidable, issues down there.
Because correct me if I'm wrong, Susan, but the hot water coil is smaller when you're using high temp than low temp. So when you're using low temperature, the coil is bigger, the fan is bigger because the pressure drop is bigger. So you need more electric needs on the fan. So there's a balance of energy there that needs to be
That's what I'm trying to say.
Yeah,
correct.
Exactly.
That's what I'm trying to say. Yeah. So you end up like you realize actually it's like a domino effect.
Correct.
Yeah.
Correct. All right, we're on the same page.
I think you're bringing up very good big picture points, is that there is a lot to consider, with the direction of your system, and whether it's efficiency, emissions reductions, and so on. That there's a lot to do a full analysis on before before making important decisions like that.
Yeah.
Again, thank you very much. All three of you. For these again, Patrick Locke of Maxi-Therm, Susan Sun Yen of ESD, now Stantec, and Tony Rinaldo of Boiler Source. This was a terrific presentation, very thought-provoking. As Patrick mentioned, you can visit Maxi-Therm in booths 42 and 43 at next month's IDEA annual conference. Speaking of which, we invite you to join us for that conference, the theme of which is District Energy for Sustainable Cities. The conference will feature a 2-day main technical program on June 18th and 19th, as well as a 1-day workshop on Monday, June 17th. And we'd love to host you for either the main technical program, the 1-day workshop, or ideally for both. The conference will also include a keynote address from Brian Deese, who is a former director of the White House National Economic Council. He was a principal architect of the Bipartisan Infrastructure Law and the Inflation Reduction Act, which I think got mentioned briefly by Tony earlier. Register now and book your hotel rooms at the beautiful Renaissance Orlando at SeaWorld. This is going to be a conference you don't want to miss. And prior to that annual conference next month, we invite you to join IDEA for tomorrow's District Energy Women's Initiative online event called Understanding District Energy. This virtual event will feature speakers from RMF Engineering, Bond Building Construction, and Austin Energy. And we hope that many of the women on this webinar can join us for that event tomorrow. There is no cost to that event. And next week, please join IDEA next Wednesday at 1 p.m. Eastern for our next Insights and Innovations webinar titled Engineering a Green Future, Retrofitting HVAC Systems to Achieve Decarbonization, sponsored by our friends at Johnson Controls. And that promises to be a very interesting and informative webinar as well. And finally, please consider submitting abstracts for presentation opportunities at our Campus Energy 2025 conference next February. The online abstract submission portal is now open, and we appreciate your submissions. So once again, to all the panelists and to everyone in the audience, thanks again from Maxi-Therm, from ESD, now Stantec, and Boiler Source, and of course from IDEA, and we will see you soon. Thanks again.
Good luck, the Bruins, Scott.
Thank you, everybody.
Thank you.
Okay.